Learn like a pro.
Have you ever looked at a chemical equation and just seen a jumble of letters and numbers? Well, what if I told you it's actually a secret language that describes a whole universe of action? Today, we're going to crack that code. We're going to take a simple sentence about a reaction and turn it into a detailed blueprint of what's really going on at the atomic level. Ready? Let's dive in.
Okay, so the key to all of this is to think of any reaction like you're looking at it through 3 different camera lenses. It's one single event, but each lens tells a deeper part of the story. First, we have the macro view on the left, which is basically just the story in plain words. Then we zoom into the standard view in the middle. That's our full chemical equation. And finally, we get to the super close-up micro view, the ionic equation, which shows us the real nitty-gritty action.
All right, let's start our journey. We're moving from our first lens to our second. This is all about translating simple words into the powerful language of chemical formulas.
To make this super clear, we're going to follow one single reaction all the way through. We're going to see exactly what happens when you mix a solution of sodium hydroxide with a solution of iron 2 chloride. So the very first step is just a direct translation. We take the name sodium hydroxide and turn it into its formula, NaOH. We do the same for iron 2 chloride, which becomes FeCl2. And of course, we do the same for the products on the other side of the arrow. This is absolutely crucial. We're turning our cast of characters into their specific chemical identities.
Now, it's not enough to just know who's in the reaction. We also need to know what state they're in. And for that, we give each substance a physical address using something called state symbols. They tell us exactly where each chemical is at, physically, during the reaction.
And here are the 4 addresses you need to know. You've got S for a solid, L for a liquid, G for a gas, those are pretty straightforward. And then there's the one we'll be using a ton today, AQ. That stands for aqueous, which is just a fancy way of saying it's dissolved in water.
Okay, next up, we gotta balance the atomic scales. There's a fundamental law in the universe that says you can't just create or destroy atoms in a reaction, you can only rearrange them. So we add these big numbers out front, like the 2's here. They're called coefficients, and their entire job is to make sure we have the exact same number of each atom on both sides. And just like that, the scales are perfectly balanced.
And there we go. We now have a complete, balanced chemical equation. That's our standard view, our second lens. But to get the real story, we need to zoom in even further. It's time to move from lens 2 to lens 3.
This full equation is great, but it kind of leaves you wondering, right? When it says these things are dissolved in water, what's really happening down there at the particle level?
To answer that, we're grabbing our microscopic lens. We're about to write the ionic equation. And the whole point of this is to strip away all the background noise and see only the particles that are actually changing.
And it all comes down to one simple, powerful rule. I like to call it the rule of splitting. It's this easy. If a compound has AQ next to it, you split it up into its ions. But if it's a solid, a liquid, or a gas, you leave it alone. It stays completely intact. That's the whole rule.
Here's that rule in action. On the left, the aqueous stuff, the sodium chloride, breaks apart into free-floating sodium and chloride ions. But see the solid silver chloride on the right? Nope, it stays locked together in its structure. It does not split. Remember, only aqueous ionic compounds split apart.
Okay, we split up all our aqueous compounds into ions. We are now ready for the most satisfying part of this whole process, making the final cut to reveal the true reaction.
So to do this, we first have to identify what we call spectator ions. And the name is perfect, because that's all they do. They spectate. They're just kind of there. They start as ions floating in the water, and they end as the exact same ions floating in the water. They watch the whole show, but they don't actually participate. So let's find them in our equation. Just look for any ion that is exactly the same on the left side and the right side. See them? Yep, the sodium ion, Na+, is aqueous on both sides. And look, the nitrate ion, NO3-, is too. They haven't changed one bit. Those are our spectators.
And now, for the final cut. We get to just cross them out, cancel them. Since they were just part of the background noise, we can remove them completely. And when we do, we finally reveal what's left.
And what's left is called the net ionic equation. This right here is the microscopic truth of what happened. It shows only the particles that actually did something, the ones that changed, In this case, the silver ions and chloride ions coming together to form a solid.
And this brings it all together on our master blueprint. Look at that journey. We started at level 1 with just words. We translated that to level 2, the balanced chemical equation. And then we zoomed all the way in to level 3, the ionic lens, to find the real core event. 3 lenses, 1 reaction, 1 complete story.
So you see, the real skill in chemistry isn't just about memorizing one type of equation. It's about being able to shift your focus between all 3 of these lenses, from the biggest picture down to the most important details. You have the tools now. So the real question is, what chemical story will you uncover next?